Hello, in the previous video we showed you how to calculate a satellite's velocity and period when in a circular orbit. In this video, I describe elliptical orbits and show you how to calculate the satellite's period and velocities at apogee and perigee. You should now see an elliptical orbit path in the image on my right. The orbit path formed by an elliptical orbit is an ellipse with two foci. The foci are shown as two dots inside the ellipse. The one on the left is larger because it is the planet, moon, or star being orbited. The other is just a mathematical construct. Actually, nothing is there. The distance between these two foci is defined as 2c. This ellipse has a major axis, the longest line going through the center that can be drawn from one point in the orbit to another, and a minor axis, the shortest line going through the center that can be drawn from one point in the orbit to another. The length of the major axis is 2a, and therefore, the semi-major axis length is equal to a, and it represents something like the average radius of the orbit. This orbit shape is described by its eccentricity, E, which is defined by the equation we show on the upper left of the screen. If the ellipse is a circle, C is equal to 0 because the two foci coincide. When this happens, the eccentricity is also 0. Therefore, a circle is an ellipse with eccentricity equal to 0. Also note in the image that the orbit point farthest away from the orbited body is called apogee and the point nearest is called perigee. Based on what you learned in the previous videos, you should expect that the velocity is fast at perigee and slow at apogee. This should be intuitive because when a spacecraft is near Earth, it must travel faster so the stronger centrifugal force can cancel the stronger gravitational force. When the spacecraft is far away, where the gravitational force is weaker, less velocity is required to cancel it. The ratio of velocities at apogee and perigee is given by the next equation I show. Here, VA is the spacecraft's velocity at apogee and VP is its velocity at perigee. Also, RA is the distance from Earth center to the spacecraft at apogee, and RP is the same distance at perigee. From this equation, you can see that the spacecraft's velocity at apogee is smaller than it is at perigee since the radius at perigee is smaller than the radius at apogee. If you want to calculate satellite speeds at apogee and perigee, you can use the two equations you now see. Compare these velocities to that of a satellite in circular orbit, which I now show. Since the velocity of a spacecraft in this non-circular orbit is not constant, we cannot find the period by dividing the circumference by the velocity. I now show the equation for the elliptical orbit period. This is the same equation we used for a circular orbit, except that we're now using the semi-major axis, A, rather than R. Remember, the semi-major axis length is like an average value for R in an elliptical orbit. We hope you found this video useful. If so, please give it a like and consider subscribing to the channel. If you want to be notified when new content is added, click on the notification bell. We plan to produce more videos in the future. We also need your feedback, so please leave comments. Goodbye.